Okay, so we'll get started. Today's seminar is an IR seminar in the Wing Group. So we're really pleased today to have Joeran Beel present his work. I've known Joeran for over a year, actually many more years virtually, through all of his work on Docear and a number of other systems related to digital library research. He and I share very similar interests in recommendations of scholarly papers, although he's much more productive in that line than I am. My group being more NLP. Anyways, Joeran is here for a sabbatical visit for the next month and a half. So if you'd like to interact with him on your projects that are related to recommender systems, please feel free to reach out to him. I understand he may be also uh, talking more with other groups in the wider Singapore area. So I'm looking forward to his talk on rethinking recommender systems sustainability and data set selection. These are topics that are very important, but are often overlooked by many of us. So without further ado, let's have Joeran take the floor. Just one final note is that this lecture will be recorded. It will be placed on YouTube. So your questions may be transcribed and used for AI model training by Google's subsidiaries, etc. Okay, so without further ado, Joeran, please.
Thank you. Yeah. There's two topics I want to talk about today. First, the energy consumption of recommender systems, an often overlooked topic, about how much carbon emissions is produced when you run recommender system experiments. And second, I'm going to talk about data set selection for offline experiments, also a topic that probably rather seems obvious. Every one of us chooses data sets on a frequent basis for their experiments. But as I will show, most people don't put a lot of thinking into which data sets they use for the experiments, and I think that's a mistake. So let's start. Before I start, let me introduce myself. Min, you did this already very well, but just a bit more context. I'm a professor of intelligent systems at the University of Siegen. I'm also on the scientific advisory board of the German Academic Exchange Service. I'm very much interested in internationalization. That's one reason why I enjoy my sabbatical here. But I'm also very open if any one of you is interested in visiting me in Germany. The German Academic Exchange Service has many great programs for foreign researchers to come to Germany. And I'm also the founder of recommendersystems.com. So if you're interested in more details about recommender systems, have a look at recommendersystems.com. Okay, carbon footprint of recommender systems. What do you think? How much energy, so in kilowatt hours, does one recommender system experiment take? Or yeah, what do you think? If you do a research paper, you run your pipelines a couple of times, how much kilowatt hours is that consuming? Give me a guess.
1% of training a llama?
Like in total, like you have your first idea, you do a bit of prototyping, then you do your entire research pipeline, you have your novel algorithm, you compare it to the baselines, you write up your research paper. By the end of that, how much kilowatt?
10.
10? Any other numbers?
2,000.
10?
2,000.
2,000. Okay, let's see later. So the work I'm presenting now is joint work based on a recent paper we presented at the ACM Recommender Systems Conference, titled From Clicks to Carbon, the Environmental Toll of Recommender Systems. We are just about to write an extended journal article. So it was joint work with two PhD students of mine, Lukas Beckmeth and Tobias Wente, and Ellen Sad from the University of Gothenburg. So everything I talk about now, if you're interested in more details, have a look at this research paper. What we were interested, and we are really surprisingly, I would say, we are some of the first ones asking these questions in the context of recommender systems, is how much energy does a recommender system require, and consequently, how much carbon or carbon equivalents do they emit? If you run a recommender system algorithm a single time, maybe on a single data set, if you run an entire experiment. By entire experiment, I mean the entire pipeline, including data pre-processing, for instance. Then a single research paper, and how much carbon is the entire community producing? Or a conference. If you conduct a conference like the ACM Recommender System conference, how much carbon is that producing? And what's the impact of hardware on this? Are there any differences between maybe Apple and an NVIDIA GPU, like an Apple CPU and an NVIDIA GPU, or other GPUs or CPUs? And what impact does the selection of data sets and algorithms have? Does that have a big impact on carbon emissions or not? And well, how was the change over the past decade? So these are the questions we tackled. And just a brief overview, what we did is we compared research papers from 2013 with 2023 from the ACM Recommender Systems Conference. And they were quite, probably not surprisingly, very notable differences. First of all, throughout all the papers, only very few researchers report on which hardware they use, which I believe is not a good thing because it just takes 1 or 2 lines to describe your setup, and I think it provides valuable information. Anyway, of those, yeah, you see it here. Can you see the mouse pointer? Yes. So in 2013, only 9% of the authors reported on the hardware, and of those, everyone used an Intel Xeon CPU. And recently in 2023, 30% and 32% of people reported on their hardware, and 100% of them used an NVIDIA GPU. And we also had in the paper, you find some details on which GPU they use. So I have the feeling that people tend to report on their hardware if they use good hardware. No one said, oh, I used my 10-year-old laptop. Something like this, because an Intel Xeon CPU typically is quite good, and NVIDIA GPUs obviously are also quite good. There's a positive trend overall. What you see is that in 2013, almost no one used any open source libraries, just 16%. That increased a lot to 2023. The vast majority of people used either some standard machine learning libraries or specific recommender system libraries. So we looked at what a typical pipeline would look like to later estimate what a typical average research paper would require in energy. A typical pipeline for recent papers is use hold-out split, grid search, and quite a few data sets. I don't know how that is in the NLP communities. On average, only 2 data sets in 2013. 4 data sets in 2023. Personally, I believe 4 data sets is still very little. Maybe we can discuss that later. And maybe also what's important to keep in mind, 2013, the recommender system community focused on rating prediction. You still maybe know this from Netflix and also Amazon. You give a 5-star or 10-star rating, and the community focused on basically a regression task, so predicting the rating. More recently, the focus is strongly on ranking. So that's more the typical information retrieval task where you have a list of 5 or 10 ranked recommendations, the most relevant documents, very similar to search in the task. What we did is we used 16 algorithms from 3 software libraries, applied them on 12 data sets, with 4 different computing systems, like a modern workstation that's like in our office, then just a laptop, 2 different laptops, and a legacy workstation that was just a very old computer we still had. And here's some of the results. So what you see here is the average in the bottom, it's the average energy consumption, so in kilowatt hours. And in the top, you see the estimated emissions of carbon equivalents in gram. So that is estimated based on the world average of how much energy 1 kilowatt hour, of how much carbon equivalents 1 kilowatt hour emits. Of course, that strongly depends on the country and what type of energy you use. And if you use solar energy or nuclear energy or coal or other energy. So what you see here is energy consumption differs a lot among the different algorithms. Probably not surprisingly, the algorithm that requires the least energy is the popularity recommender system. That's very easy to calculate. You just basically count what is most popular in the data set. That's here the total average. So all these algorithms on average require half a kilowatt hour to run a single time on average on one data set. And here in the top, you see this is all deep learning algorithms, but you still see more here in the middle that there's like an overlap. So also here, I think that's also a deep learning algorithm. So it's not that all deep learning algorithms require a lot of energy and all the traditional algorithms require very little bit, but you see a tendency that the old traditional like KNN popularity require rather little or very little energy, and deep learning algorithms require a lot. Each point here that you see is one data set. So also what you can see here already is, depending on the data set, energy consumption differs a lot. And if you just look, well, at the top line, like this data set requires obviously much more energy to this algorithm than the average. Like, I don't know, factor 6 roughly, I would guess.
Do you want to point with the mouse?
Yeah. Yes. So just if you compare this data set here, that's an outlier with the highest energy requirement for this algorithm with the average, I think it's the median here, which is roughly 500, and this is about 3,000, or in kilowatt hours here, around 6 versus 1 point something. So it's factor 5 or 6. You can see this easily here.
So just to double check that the x-axis is the same between the caption and the bottom and the top, right? These two are equivalent.
Yes, they're equivalent.
Okay.
It's just this is kilowatt hours, and each kilowatt hour exactly on average is, I think, 500 grams roughly of CO2.
I see.
So it doesn't matter if you look at the bottom or the top.
Right. Okay.
So what you see here already is the difference between different algorithms is quite notably large. If you compare the most simple, the cheapest algorithm popularity with the most expensive algorithm, Macrit VAE, the factor is 255. That's a lot. And popularity is very good, often, not always. But I mean, you see that on news websites, you see it on Netflix. On Netflix, popularity recommendations are everywhere. Now, I'm not sure if it's because recommendations are good or because it's just so cheap, because companies care about electricity usage. I mean, if you have a factor of 255, that's a lot of money if you are Netflix. If you can save 250, like factor 255. And there's some other research paper. I don't have the title in my head, but it's like that's one, I think it's the only paper that was published prior to ours 1 year ago. They show how the effectiveness of recommendations or algorithms improves based on energy consumption. And I think the conclusion is it's not really worth so far. So you need a lot more energy, but you get hardly any improvements, if at all. So next, let's look at the data sets. So this is the algorithms. Let's look at the data sets. What you see here is very similar to what you saw with the algorithms. Based on which data set you use, a lot more energy is required. So what you see now here is a number of recommender system data sets and the average or the box plot for the energy consumption of the 16 algorithms that we applied. So similar here, so this is the median here. You see that the median average energy consumption for Yelp is the highest and much larger than for smaller data sets like Hattrick or MovieLens 100K. The factor here is up to 1,500. So if you compare the average electricity required on the Hattrick data set compared with Yelp, it's factor 1,500. So the impact of the data set is even stronger than the impact of the algorithm compared for energy consumption. Obviously, there's a strong correlation between dataset size and energy consumption. The larger the dataset in the tendency, the more energy. It's not a perfect correlation. I forgot the number, it's in the paper. So it also depends on how you measure size. We measure just the number of interactions, so basically the number of rows in the data set, and of course the number of features and the type of features also has an impact. But I think what you can take from here is you need to think about if you really need such large data sets. I think we did some side study, especially for simple algorithms like popularity or KNN. You don't need to let that run on this. If you take a small data set, you get basically the same results. For deep learning, of course, the more the better, typically.
So for this graph, I noticed there's usually 2 or 3 outliers. Are they due to the same algorithms? Do you know?
So here, each point is a different algorithm.
Right.
So you see that, that's just the average on this data set. And then you have some algorithms that need a lot more energy.
So I'm asking whether the outliers, are they due to the same algorithms, let's say very complicated deep learning ones, which showed up on the top of your last chart?
I can only guess. So looking at this, frankly, I don't know out of my head. So it's probably these algorithms that are the outliers. I don't know out of my head if they are all like the same type of deep learning. Yeah. But I really like some of the pictures they're created with ChatGPT and Mistral. I found, I think the first one, I don't know. Mistral is getting quite good with text here. It's not too bad, right? I mean, you probably know with ChatGPT, if you, and you see that later on some other images, like the text, the words are just really bad and messed up. And this is pretty good. Not perfect, I think, but pretty good. Anyway, so back to one of the original questions. How much energy does a single paper require on average? And what we did, as shown before, is we looked at an average research paper, and we found that they use 7 algorithms, 3 data sets, 16 configurations with grid search, so relatively small number. But anyway, and as you maybe remember, an average experiment requires, or an average run of one algorithm on one data set requires on average half a kilowatt hour. So if you multiply 7 algorithms by 3 data sets by 16 configurations, you get for a single paper 170 kilowatt hours of a single run. But then if you think about, so that would be the energy required once everything is finished and you do your final run for your paper. And maybe so ignore this. If I ask you, how often on average do you run your experiments before you write your paper and before you have your final results? Like, I'm just really curious in your estimate. If you think from the first idea and then all the iterations you do, how often on average would you run your experiments? I mean, you have the first prototype, you see, oh, there's a mistake. Then you run everything again. Then you think, oh, I need one more baseline. You try to run the baseline, it doesn't work. You tweak it, then it works.
At least 10.
At least 10? Yeah. Yeah, personally, I think much more often. What we did is we were recently at the DAX seminar, and luckily there were the developers of a few recommender systems libraries from Elliot, RecPack, and Lenskit, and also some practitioners who develop recommender systems. We asked them, and their average guess was 40. I don't know out of my head what the range, I don't know the minimum and the maximum. It's probably in the paper, but I think that's quite realistically 40 times. And if you then take 171 times 40, and even if you just think 10, you have quite a large number. So when you guess 2000 in the beginning, that's pretty close, I think, of what this. So based on our estimate, it's a very rough estimate. It could be much higher depending on your data set. It could be notably lower, but as a ballpark number, if you produce one paper about recommender systems research, I think very roughly, you can estimate that you require about 6,800 kilowatt hours. And that is a lot. That's really a lot. And then if you think of a conference with 100, 200, 400 papers, and then all the participants going there by airplane, so that's also really a lot.
How much would that be equivalent to, like 6,000 running, how many homes?
It's like so how much that will cost? In Germany, I think 1 kilowatt hour is about 30 cents. That would be about 2,000 euros. Yeah, that's a lot. That sounds really like a lot, 2,000 euros. But like we always run our experiments on a cluster, on the university cluster, and I don't know. I should ask them what their electricity bill is. But yeah. And I think this, of course, it could be much lower if you do a simple paper where you just have 2 or 3 algorithms, like, and then K and N and popularity as a baseline, and then your own algorithm. But it could also be much higher if you focus on deep neural network research. And the data sets that are being used here are still relatively small. This is kind of pre-LLM research. So I think if we would do this now again or in 1 year again, and because right now everything is LLMs on recommender systems conference and probably everywhere else as well, and we would train our own models, okay, this would be gigantic. So the key findings from this is, on average, let me see. On average, the CO2 emissions increased from 2013 to now by factor 42, from around 75 kilos to 3,300 kilos for one paper. That's a lot, factor 42 in just 10 years. And that is based due to the fact that people use more algorithms now as baselines. They use more data sets, like from 2 to 3 or 4. And the algorithms require more energy. Then I'm going to, so I'm showing, I have a few more slides. So what we also found, I show that on one of the next slides, is the Apple M1 chip, and I assume also the M2 and M3 and M4, but we just had the M1 chip, is much more efficient than an NVIDIA GPU. So, and it's much slower, but in the end, you have the same model, like you have the same performance. So if you are patient and you don't mind if you train in, well, I don't know, in 1 day or 10 days, or in 1 week or 10 weeks, or you just build a big cluster out of M1 chips, you could save, it depends on the algorithm, but in some cases, you could save up to 90% of energy. That's pretty impressive, I have to say. Yeah, and then we had this and this already, like factor 1,400 for the data sets, factor 257 based on the algorithm. And then in extreme cases, of course, it's a really extreme case. But if you take the most energy hungry algorithm on the largest data set and compare it with the least energy hungry algorithm, so popularity, on the smallest data set, the difference in energy consumption is factor 134,000. So I believe it's really crazy numbers that show how important this is to look into this. And I mean, we are not saying, okay, everyone now should only use popularity on the smallest data set as a benchmark, or as baseline. There is good reasons to use large data sets, and there's good reasons to use deep learning and complex algorithms. But I think these numbers show it's worth looking into this into more detail and think about, can we somewhere save energy without compromising too strongly on the performance? Yeah, I'm not going to details here. I reference, have a look at the paper if you're interested in more details. This different algorithms in the different libraries, sometimes also the same algorithms in different libraries, once run on a CPU, once like KNN, and once run on a GPU, and then the performance measured by NDCG. So I'm just surprised NDCG is anyway. I would have to look up this in detail myself. And this is the comparison about Mac and other GPUs. Again, I'm not going into detail into this, but if you're interested, have a look at the paper. It's showing you like the training time and then the efficiency. One big factor I just briefly mentioned before is where you run your experiments. It makes a huge, and then this is the electricity. So this is not our chart, or I should have put some reference there. So this is not from us. This is just copied from the internet. It just shows how much, sorry, this is from us created, but it shows the estimated carbon emissions based on where you run your experiments. And in Sweden, for instance, because Sweden is basically solely relying on renewable energy, the carbon emissions are very low if you run your experiments, in contrast to Asia, or basically also all other parts of the world, where carbon emissions are much higher because, at least on average, not so much renewable energy is used. So if you want to do something good for the environment, run your experiments in Sweden or some other countries, or in a data center in your country where green energy is used. So what to do? And I just want to show you a few other things. I'm not talking into detail now. We have recently published a few other papers. Green recommender systems, a call for attention, where we just explain in more detail why we believe the recommender system community should put much more attention on this topic. We have introduced a tool. It's a demo. I think we also presented that at RecSys. It's a demo that allows you to measure easily the energy consumption of your experiments, because that's, I think, the first step. That there's better tools that allow you easily to measure how much energy do you use and to report that in papers. Now that's the first step. And then we can think about how to reduce this. We have proposed one or two methods that we believe will save energy. One of them we call E-fold cross-validation. It's an alternative to K-fold cross-validation. And it's a dynamic approach that chooses the size of K based. So how can I explain that quickly? With K-fold cross-validation, you always have a fixed number of K, 5, for instance, or 10. But sometimes we found it's not necessary to always have 10 folds. Sometimes you see already after 3 or 4 or 5 folds that the results you obtain in the individual folds are very stable. Like if you obtain already 4 times more or less the same results, you don't need to repeat that another 6 times. Chance is extremely high you will get just 6 times more the same results. So this approach is looking at the variance between different folds, and if a certain threshold is reached, the training is stopped. Any questions so far before I go to the second topic?
I have a question.
Yeah.
So I see the same or similar paper on RecSys 2023. Is that published?
Yeah.
Okay.
No, so there was one paper in 2023 that's not from us. That was the very first paper about carbon emissions and recommender systems. We published this in this year, 2 months ago.
Yeah. So I talked to the author of the paper published in 2023. So actually I asked him a question. I say, here when you do the simulation of carbon emission, right, you only simulate the process of training. But actually, this is not a closed loop of recommender system. The recommender system, after you train them, right, you are designed to serve the people, to save people's time on searching or browsing, right? So you should do a very comprehensive simulation. For example, if you train this model, how much time can you save the users on browsing or searching for certain results? That if the algorithm is simple and easy to train, right, it produce very very few carbon emission, but at the end, the people, the user may use the system for several times, then generate a lot of carbon emission at the other end.
Yeah,
so
very
yeah,
good point.
yeah. So can we try to simulate the whole process so that we can give a very concise number? For example, the big company just need to train the algorithm for once, and it serve millions of users and save a lot of energy in browsing. But is that worth the time of training? So
It's a very good point. Yeah. So our work and also the previous work, we focus on the research, and once the paper is written, finished, basically. And of course, there's much, I mean, the real important part comes after that. When the model is used in production, what happens then? How much energy is that using? Or what you said, is it worth maybe spending more time in the training, but saving time or energy later? Yeah, very good point. That would there's lots of things that could still be done. And I think the machine learning community has started with green ML already a few years ago. The recommender systems community is lacking behind. Yeah.
Hi, Prof. Joeran. That's another question about the relationship between performance metric and the energy consumption. Do you think they are linear or
No,
performance will
not at
be
all.
better?
So we did not look so much into this. That was last year already. There's very little, if at all, performance gains by having, but that's a general problem with recommender systems, that there was also a good paper by Dietmar Janach a few years ago, that there's hardly any progress in the recommender systems community. There's a lot of, this is a recorded video, so I need to be careful what I'm saying. But the evaluation practices in the community lack some rigor, to say the least. So, yeah, but that's a completely different topic besides energy consumption.
So in short, we said that increase the energy consumption, we don't linearly get gains in the performance gains, right? No.
So far, it looks like that. But I mean, I have no doubts that there will be more and better algorithms in the future, and very likely they will require more energy than today's algorithms. But I just have no idea if it's okay. There's so much noise that I would not say it's linear or not linear. There's just a lot of bad work out there, noising.
Cool, thanks.
Yeah, so I just want to riff on Victor's first question, which is that inference versus training costs are different, which you've already acknowledged. Yeah. But then he's also interested in, like, say, a holistic evaluation of the amount of savings that recommender systems produce.
Yeah. I fully agree that that's another problem of the recommender systems community. We use NDCG, we use precision, maybe click-through rates sometimes, but yeah, the user experience is in the end what counts, or maybe profit of businesses. And it would be very interesting to measure that as well. But as a researcher, it's very difficult to do that. That would be, I think, up to the companies who implement that in their systems and evaluate.
So speaking as somebody in the NLP community where there are model cards and things of this sort, do recommender systems now have model cards or data set cards such that, you know, downstream practitioners like industrialists, do they have access to information like this about how much carbon it costs, etc.?
No, not that I know of.
So there's no standardized way of presenting green information?
No, not at all. There's no standards. I mean, this is like the second paper about green and recommender systems at all. So there's no awareness so far.
Okay. That's a very timely topic.
Yeah.
How confident are you in the improvements in hardware in the future? Because you said that there may be a 90% savings if you wait long enough.
Yeah.
Maybe as hardware improves, it becomes lesser and lesser of a problem in terms of energy consumption in the future.
I think hardware will become more energy efficient, but I also believe that algorithms become more and more complex. I believe you see it with LLMs. Of course, on the one hand, companies try to somehow prune and like make their large language models more energy efficient. On the other hand, there's more training data. There's novel algorithms that become more complex, and I think there will never be really enough energy. Like if you have a very energy efficient algorithm, you could still run it in parallel probably on many, many machines and just get faster training times. And then you think, oh, I think there was some really interesting work that showed that only because an algorithm becomes more efficient doesn't mean that energy will be saved on a global scale. Because if an algorithm becomes faster, so more efficient, also typically means faster to train, or you can parallelize it and it becomes faster, that means more companies want to use it, or more users want to use it more often. So of course there's a benefit, but not necessarily in saving energy. Good. Okay, then let me get quick to the second part, dataset selection for offline experiments. And that picture is also created by Mistral, and I think that's quite funny. Typically, ChatGPT is a bit more boring. So this topic is about how can you choose out of the many, many data sets the ones you should use for your recommender system experiments. And let me ask you, how do you choose data sets for your NLP experiments?
Maybe just follow previous work.
Yeah.
I know it's a wrong answer, yeah, but
yeah,
probably a good correct answer.
Yes, you just follow previous work. You just look at some other papers, or maybe you did some reviewing of conference papers and you just see what they use.
So that's comparable. Yeah.
Mm-hmm. Yeah. That's probably what, is anyone doing any other practice?
Like you check if they have the labels or annotation that we require.
Yeah, obviously it must have the information that you need. Yeah.
Already like very few data set can satisfy the requirement.
Yeah. So this is a typical recommender systems research paper with some of the most, that's actually our paper about energy consumption. It's the data sets we used, and that are some of the most common data sets. And what we had a look at recently also was we surveyed 41 papers from past year recommender systems conference. We were interested in finding out how do researchers choose their data sets. And 24% just say we use this data set because it's public or real world. They didn't say we used it because it was public. They just said we use this data set, it's public or it's a real world data set. Some people mentioned the application domain, or this is a news data set. So obviously they wanted to create maybe then a news recommender system. And 44% also said, oh, we use this data set because it's widely used. So that's what you said, or it's a benchmark data set. I'm very skeptical about the term benchmark data set in recommender systems because there is no agreed benchmark in recommender system. And I believe it's also almost impossible to have a benchmark data set because recommender systems is so broad in its application. On the one hand, first of all, you can treat almost like if you look at the recommender systems conference, of course, there's movie recommendations, news recommendations that are like the traditional recommender system domains, e-commerce. But you could see Google Maps as a recommender system. Right? It recommends you the most fuel efficient route, something like this. So there's not the one benchmark data set that you could use. Anyway, all of these things are not real justifications. There is some merit in using data sets that other people use. Like you said, it allows to compare your results roughly with the results of other researchers. So let's say it's one good reason, but we believe there's certainly more that should go into the decision which data sets to use. And so far, nobody really seems to care. I'm not aware of any big discussion or guidelines how to choose data sets or which data sets to use. And we wrote, this is also based on a research paper we recently published, also at it was a poster, I believe, at ACM Recommender Systems Conference. So let's talk first about what is the goal of choosing data sets. How can I black out my screen so that we can discuss this? I just go back. I ask you to make it a bit more interactive. What's the goal? Why do you choose very likely multiple data sets?
Yeah, actually, I'm working on some vertical domain recommender system, like fashion, music. So if in this domain, there are not too many choices. We can only use like a Spotify or Last.fm for music recommendation. And for fashion, we can just use the clothing or apparel stock data set of Amazon or like Alibaba, the iFashion, such kind of. Not too many choices.
But even there's not too many choices, I assume most of the time you use more than one data set, right? So why? I think the reason why is simple. You assume that if you take a relatively large number of data sets, your algorithm performs well. It will also perform well on new future unseen data sets. If you use 3 data sets from fashion, your algorithm performs well. You assume your algorithm will also perform well on some other fashion data sets or some other, like in real world, real production recommender systems. That's the basic assumption why you choose probably more than one data set. And then maybe you choose only fashion data sets if you have a very specific algorithm that is for fashion. Maybe you have a generic recommendation algorithm where you use e-commerce, movies, because it just works for everything, or almost everything. So keep that in mind. If you choose data sets, you want to do that because you believe or because you want your results to be meaningful or representative or generalizable, reproducible. There was one other paper, I think again 1 year ago, so we are never the first ones really, always the second ones looking into some topic. I think 1 year ago, these authors presented the probably most intuitive solution, or they looked into the most intuitive idea of choosing data sets, and that would be to choose different data sets. If you want, and that's what most researchers and recommender systems want, if you want an algorithm that generally performs well as a recommendation algorithm, you should test it on different data sets. And by different data sets, I do not necessarily mean, or also they don't necessarily mean e-commerce and movies, but maybe have some features like the size of the data set, the sparsity, the type of features. And if you then have 5 different data sets that differ in size and sparsity, in the type of users, the domain, and your algorithm performs well on these 5 data sets, that's, I think, a good indicator that your algorithm should perform well on other data sets as well. So I think that's a reasonable assumption. And the problem is it holds not true. So if you think about, so that's what you would be doing. You would have an n-dimensional feature space. Feature 1, sparsity, feature 2, maybe number of ratings, and you plot your data sets in the feature space. So this is data set 1, 2, 3, 4. And your assumption would be, okay, if these 2 data sets have similar features, algorithms should perform similar. So for your experiments, you probably would not choose these 3 data sets because your assumption would be if your algorithm performs well here, it will also perform well here. So maybe you would choose this data set, this data set, this data set, and this data set. And if your algorithm performs well, you would assume it will also perform well here and here and here. I think that's a valid assumption, but also as the results of these researchers show, it's not really true. Only because data sets roughly look the same doesn't mean that algorithms will perform the same. So how to do better than this? Let me first show you some, like from a real world recommender system, because that's some work we did a few years ago. We applied 5 different algorithms here, 1, 2, 3, 4, 5, on one news website. That's the local Cologne newspaper. And we got these results. So this algorithm here was best, user-based collaborative filtering. Popularity performed very poorly. And we applied it on the second website. So this is all German news websites, different domains like local news about a city. This is sport. We applied it on some other website. And you see already the algorithms perform extremely different on each website. So which algorithm would you choose on a new website? Again, maybe a German news website. You can't tell by the dataset characteristics. And it goes even deeper, the problem. If you just take out one website and you look at this one website and you look at the time of the day, algorithms will also perform differently. So at night, a different algorithm performs best compared to during the day. So it would be very hard to choose an algorithm. So our proposed approach, and it's not the final answer, but I think it's a good idea. Our proposed approach is what we call algorithm performance spaces. So this here is the traditional idea, I call it. Yeah, you have the features of the data sets. We have a space with performance of algorithms. And now you need to think a little bit because it's a complex graphic, but I try to explain it. So we would have a number of data sets. Yeah? The orange dots are data sets. We have a high dimensional space. So in this case, just 2 dimensions. We have 2 algorithms. Algorithm A1 here and the performance. Performance can be anything, but for now, let's say NDCG. And here's the second algorithm. So what it means is on this data set, algorithm A1 performs poorly. It has a low NDCG. Algorithm A2 performs very well. It has a high NDCG. And we argue that this would be much better for choosing data sets. You take a number of algorithms, benchmark algorithms, 10, 20, create this algorithm performance space, and you use that to choose data sets for your experiments. The assumption would be, and you choose data sets that are far apart from each other. So the assumption would be, if the existing algorithms perform like this, one moment. So let's say you pick this data set, and your algorithms will perform in a certain way, then you could conclude your algorithm will perform in the same way on this data set. I show that on the next slides. And this would also help to pick challenging data sets easily. On these data sets, all algorithms perform poorly. So if you develop an algorithm that performs well on this, that would be a real advancement of the state of the art. These are kind of solved problems. All algorithms perform well already on the data sets, so it's not really necessary to evaluate your algorithm on them because there is enough algorithms already out there. So what we did is we took 29 algorithms, 95 data sets. That's the orange dots. We highlighted the movie lens data set variations here with the crosses, and the triangles are Amazon data sets. And because we cannot visualize a 29-dimensional space, we just always took 2 algorithms. So what you see here, this movie lens data set, you see that this algorithm performs reasonably well with probably around 0.6. And this algorithm performs relatively poor with maybe 0.3. So that's the algorithm performance space with these 2 algorithms. Here's 2 other algorithms where you see that the algorithms perform almost the same. And here you see again 2 other algorithms where you see that this algorithm is much better than this for all data sets. So you could now also argue it's not necessary to have both algorithms here. One of them would be enough. And here this apparently is very poor algorithm, so you don't need that as well. We reduced the dimensions to just have a visualization. So with PCA, we reduced it to 2 components. And we propose that researchers should use this to choose data sets for their experiments, ideally from different areas. So maybe 1 or 2 data sets from here, 1 data set from here, 1 data set from here, 1 from here, because we don't know anything about the data sets. I don't know how big they are, how many features they have, but we know algorithms perform differently on them. So if you manage to develop a novel algorithm that performs well on, let's say, the majority of these few selected data sets, that's a real advancement.
So I
yeah.
have a question for this. This one is a PCA or some type of dimensionality reduction on two components, right? So component one is explaining 91% of the variance. So that means that the ones that are measured on component one, they have a lot more entropy in terms of performance. Is that right?
They're much more, let's say, meaningful. So maybe it would be better to not make it as a square, but skew this axis to show the importance of this.
Right. So you're saying the ones that are on the right side of the chart are more diverse in terms of their performance with respect to different algorithms.
Yes, exactly. Yes.
Yeah. Okay.
Yeah.
I see. And so crossing this with your first paper, does this mean we should also calibrate for energy consumption?
Yeah, that would be a next step to think about how we can integrate energy consumption. One simple reason would be, well, just to color or whatever the energy consumption. And then my argument would be both data sets are very similar. If one uses a lot of energy, the other one uses little energy, there's no reason to use the one that requires a lot of energy because both are highly similar. And the hypothesis is new algorithms will perform similar on them.
But you also argued in one of your earlier slides that you can't predict from a particular data set which algorithm will do better. Right?
Exactly.
So then we couldn't necessarily make the inference assumption that even if the data sets are similar in personality, similar in terms of their performance characteristic, that they might still behave similarly across a new data set or across a subset of the same data set.
And right, that's a very important point, and very important to distinguish. Based on this proposal, we cannot estimate in general how well an algorithm, so let's just stick with this example. We cannot estimate how well an algorithm will perform on any of these data sets until you run at least an experiment on one of the two data sets.
Okay.
So only because this is here, it doesn't mean it's difficult or an easy data set. Our hypothesis is, let's go back to the illustration. So it's difficult to explain. If you have a new algorithm, you would have a new dimension, right? Yeah. So if you run your new algorithms on this data set and the value you receive would be similar to algorithm A1, then I'm stuck now. So
maybe I can try to paraphrase.
Yeah.
So you're saying in this algorithm performance space that if a new algorithm that is invented performs correlated to an existing algorithm, that it forms sort of like a neighborhood around that performance area, right? So you're saying that these two algorithms, since they're performing comparably over certain data sets, one is substitutable for another. Are you saying something like that?
Exactly. So you must keep in mind that this normally would be a high dimensional space with 20 algorithms, maybe more. And if you pick then 2 or 3 data sets and your novel algorithm performs similar to some existing points in there, you could conclude that it will also perform similar on unseen data sets. We still must prove that. So we have some first, this was like an exploratory study where we just plotted this and then we had this.
Right.
The next step would be to look into if the hypothesis is really true.
Right. Yeah. To correlate it against your previous German newspaper forecasting study, because that seems to prove a contradiction, right? To say that similar algorithms performance on some parts of the data set, even on different time periods or sub-selections of those data sets, subspaces of the data set may not perform consistently.
Yeah, exactly. Could be, yeah.
Okay, got it.
Good. Okay, I think time is up. Any more questions?
Questions from our speaker? Let's first thank our speaker.
I have a question about the